video, we're going to try and answer the question of what is light. We are all aware that light is all around us and we see it every day. But have you ever thought of what it's actually made of? Does it weigh anything? How does it get from one place to another? Or is it just everywhere? We know from our experience every day how important light is. We use it to see. But did you know that a different type of light is responsible for us being able to use the radio, for radar, to microwave food, to heat things, to tan, to have x-rays taken, and so on? The world would be a very dark place without light. But what is it? This is a question that physicists have been trying to answer for centuries. To answer the questions we asked at the beginning, physicists came up with two different ideas. Maybe light consists of waves that radiate in all directions, or maybe light is made of particles and stuff we can see. Very early on, it was known that light had wave-like properties. And Descartes, who was famous for saying, "I think, therefore I am," therefore thought that light consisted of waves. But what are these wave-like properties?
What we're going to do is look at waves in water. Here I have a tray of water and we're going to create straight waves with a straight object, like so. If we put an object in the way, we can see that the waves reflect. There's another phenomenon that we can observe, which is called refraction. If we make the water shallower by putting this plate of glass in the tray and create waves that run over it, we can see the slight bending of the waves as they pass over. This is because the water slows down when passing over the shallower water. We'll come back to our water ripples again later. So this shows wave-like properties with water waves, but as Descartes realized, light does similar things. So here we have the setup of this experiment. Here is a laser pointer and it's shining a beam of laser light at this large block of glass. And the glass has got some internal etchings, as you can see there. What's happening is that we're seeing both reflection and refraction. We're seeing reflection from both the surface of the glass, as you can see there, and we're also seeing reflections from the internal etchings. We are also seeing refraction, so if I use this smoke machine, we can see the path of the laser going both in and leaving the block. And you can see the light that is being passed through the block has been bent slightly. What I'm going to do is I'm going to mark the position of the laser light. So if the block is taken away, we can see the position has moved. The difference that we see here is the amount that the laser light has been refracted or bent by the block.
Despite this, some people still thought that light consisted of particles. Isaac Newton, here he is, the same man who discovered the law of gravity after the apple fell on his head. As a side, this is almost certainly not true, which was one of these. He thought that because light travelled in straight lines, it was better described by treating it as particles. He called this a corpuscular theory, because corpuscle is another word for a particle. Another famous physicist called Laplace used this theory to predict something that was so massive that light could not escape from its gravity. Nowadays we call this a black hole. People argued about this for the next couple of centuries, but slowly the argument swung to the wave theory. The only problem was that waves needed something to go through. Water waves need water, sound waves need an atmosphere and an object to travel through. What about light, which they knew could pass through nothing, a vacuum? How did that work? To try to explain this, physicists came up with what they called the luminiferous ether, which existed everywhere but we could not detect or see. This puzzle was solved in the second half of the 1800s by two physicists who lived at the same time. An English physicist called Michael Faraday worked in the field of magnetism and worked out that light under some circumstances could be influenced by a magnetic field, so had to be related some way to the new field of electromagnetism. A very great Scottish physicist called James Maxwell took these ideas further and created a mathematical model for light. These are his very famous equations, called Maxwell's equations, where light consisted of vibrations or waves of electric and magnetic fields, which could exist in a vacuum. The existence of the ether was disproved by a very famous experiment by two famous physicists called Michelson and Morley. We won't go into this today. So the electromagnetic theory determined that the waves of light were waves of electric and magnetic fields. Job done, we can all go home. However, as the 20th century came along, it was really some things didn't fit. Firstly, there's a phenomenon known as the photoelectric effect. It was known that some substances emit electrons when electromagnetic radiation, like light, shines on them. The number of electrons and the energy of these electrons emitted does not depend on the amount or intensity of light, which you would expect if it was a wave. If it was a wave, then dim light left long enough shining on a substance would store up enough energy to eventually release an electron. In fact, this never happens, and whether an electron is emitted or not, and how much energy the electron has, depends on the frequency of the light and not how strong it is. This bothered a very famous scientist called Albert Einstein. Here he is looking bothered. He proposed that light consisted of swarms of particles, again, which he called photons. Only if the particle has enough energy, which it could then pass to an electron in the material, could an electron be emitted. He got the Nobel Prize for this. Nothing to do with E equals mc squared. This was the birth of quantum physics, or quantum mechanics. Work on the different applications of quantum physics took up the rest of the 20th century and still continues today. Another interesting phenomenon is the phenomenon of light pressure, in which it is known that a beam of light will apply pressure to a surface that it shines on. This laser that I'm holding is actually exerting a pressure on this toy. This could be explained by thinking of the light particles as bouncing off the surface and so exerting a pressure, although this in fact can also be explained by electromagnetic waves. It's a very small effect. This laser will exert a tiny force on this guy. It would need about 50 billion lasers to hold up this guy against gravity. Nevertheless, in a big scale like space, light pressure is responsible for some of the motion of asteroids, where all other forces are very small. When we send probes to Mars, we have to account for light pressure when we calculate the path of probes between Earth and Mars. It could potentially be used to propel ships through space. In fact, an experiment has already been done successfully with a satellite called LightSail, which is a little cubic satellite about the size of a PC that can deploy a light sail of area about as small as a small swimming pool. So sometimes waves behave like a particle. So is it a wave or a particle? In fact, it's both. Let's go back to another experiment that seems to show wave-like behavior in light, which is important when it was decided that light was waves.
When I create two sources of waves with my fingertips, we can see a pattern of wave peaks and troughs. When two wave peaks or troughs come together, we get a bigger peak or trough. When a peak meets a trough, they cancel out. We see the same effect in light. Here I am shining a laser through two slits in a piece of card, and we can just see a light interference pattern of light and dark bands.
How does this fit with the idea that light consists of particles? Well, we can justify it by saying that light particles, or photons, are in fact little packets of waves, so many photons might interfere with each other, so we're still happy with our previous answer. However, if light behaves like particles, then if we make the light source weaker and weaker and weaker, we will get to the point where only one photon is passing through the experiment at once. We would expect each photon to just go through one slit or the other, wouldn't we? We would think that the pattern would just look like a shadow of the slits that each photon is passing through. In fact, we can do this experiment by using a laser and reducing the amount of light through lots and lots of different layers. And this isn't what happens. This is what happens. Each dot that we see is one photon appearing on the screen and being detected by a very powerful detector. We can see that slowly the same interference pattern as before is building up with each photon. It looks like the photon is interfering with itself. The photon must be going through both slits at the same time. This is weird, and it puzzles scientists a lot. The photons can be going through both slits. Let's put a detector at the slits so we can find out which slit the photon is passing through. Well, if we do that, the interference pattern vanishes altogether. It's like the photon knows we're looking. This problem is at the heart of quantum physics. As a very famous physicist called Richard Feynman said, if you think you understand quantum mechanics, you don't understand quantum mechanics. So, to finish and answer the questions at the beginning, light behaves as if it consists of waves or particles. In some circumstances, it's better to think of it as a wave, in others, a particle. And our final question, photons do not have any mass. Thank you for watching my video! Bye!